Hello.
Hello. Can you hear me?
Yes, you are audible.
Okay. So let me share my screen. Um, just a minute. Can you see my screen?
Yes, the screen is visible, but it would be better if you go to the full screen mode.
Yes. Is this okay now?
It has not changed, but we can go on with this.
Just a minute. Now
No, it's the same.
it's the same. Is the screen changing?
Sorry?
Was the screen changing?
No.
There seems to be some trouble. Just a minute. Maybe I share my entire screen. Now is it better?
It is better.
Yeah. Okay. So let me go with this. So yes, good afternoon, everybody. First of all, I begin by thanking the organizers for giving me this opportunity to speak in this very nice series of talks, having a very diverse list of speakers and topics. It's a very innovative and very new and very useful for everybody. So this talk, as Anindo said, will be about the interface between quantum information and few and many body physics. And yes.
I'm interrupting a bit. If you could hide the small message at the bottom of your screen. There is a
Yes, that is. But the trouble is that I don't know how to do that.
hide. Just
But
stop sharing. There is something written as hide.
yeah, but I don't find my cursor. That's the main trouble.
Oh. Your cursor is showing on our screen.
Cursor is showing on your screen, okay, but it is not showing on mine.
Okay,
Why is it that?
okay, it is just a minor thing, maybe.
No, but still, it is sort of. It would be nice if I can. Can you see my cursor? Where is my cursor?
Your cursor is at where it is written QIC group. Just to the
QIC group.
just to the
Okay.
left of.
Okay. So now is it below hide? Tell me
No.
when it comes to hide.
Okay,
Where is
right
it now?
to the right. Move to the right.
Yes.
Move to the right. Further right.
Yes.
Right. 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 A little above. A little above. Left. Left. Left and above. Left. Left. Click. Click. A little
Uh-huh.
below. A little below. Below.
No, but no, but it stopped the sharing.
Okay.
It's hide.
Okay.
Uh-huh. Just a minute. It's I stopped sharing. Start again. Window. Is this better?
I don't see your presentation right away.
Do you see my presentation? You don't see it?
No.
Uh-huh. Why so? Can you see now?
Yes.
Is it full screen?
No.
Yeah. So my internet connection got, so sorry. Can you see my screen now?
Yes, yes.
Yes. Okay. Okay. Yeah. Sorry for this fiasco. Yes, I will be, as I said, I will be talking about quantum information and its interface with many-body physics. There is a small thing on this first slide written in a script that I don't understand. It is a Sikkimese script and language. I got it with the help of Onindo. And then, of course, this is in Devanagari. And these are the people who helped me in preparing these slides. Okay. Yes, this person, of course, everybody knows. This is Marie Curie. And this little girl, still a teenager, is also Marie Curie. So the status of the bridge between quantum information and many-body physics is something like this. It's a person full of possibilities is meeting a person who is who has already proved her possibilities. Yeah, so to make it slightly complete, we will have a few slides on quantum mechanics. So, of course, this is the title of this slide is very sort of obnoxious, maybe. But I will just set some notation, nothing else. Of course, this is not a course. So, as we all know, that situations in a physical system in quantum mechanics is described by vectors in a linear space. By linear, we mean that these vectors can be added and these vectors can be multiplied by numbers. These numbers will be complex numbers. Moreover, these vectors have an angle defined between them. So I can talk of the angle between two vectors in this space. So we consider such a space, and every situation in our physical system will correspond to a vector in that space, and vice versa. This linear space in which there is an angle defined is called a Hilbert space. Of course, this is not the correct, proper definition. It's correct, but not proper definition of a Hilbert space. But we will live with that for brevity. We will often talk about two-dimensional complex Hilbert spaces. They represent, for example, the spin of an electron, and they are called qubits, quantum bits. Now, if we have a Hilbert space of two physical systems, then we will take a tensor product of the individual Hilbert spaces. So two physical systems, if they have Hilbert spaces H1 and H2, then the joint Hilbert space of the joint physical system is H1 tensored H2, tensor product H2. Okay. Solids, for example, paradigmatic many-body systems can often be represented as an array of electron spins for some purposes. These two statements constitute what can be called quantum statics. This is not a standard terminology, just for the sake of this talk, maybe we use it. And then there is dynamics, which says that any physical system, when it moves from one situation to another, then the corresponding vectors move from one vector to another, and this movement is generated by a unitary operator, is governed by a unitary operator. And this is what is our quantum dynamics. And this is not how we read about quantum dynamics in textbooks of quantum mechanics, but we usually read about the Schrodinger equation, but these are equivalent statements. And then we come to measurements. And for measuring in quantum mechanics, we use a basis. Measuring onto a basis produces one of these basis states. This basis is the basis of the linear space, of the Hilbert space that we have been talking about. And the production of this basis, the production of these outcomes of this measurement are completely random. This is also an assumption. But they appear with definite probabilities. This is quite similar to when you toss a coin. The appearances of the head and tail are random, but they come with definite probabilities depending on whether the coin is biased or not. If it is not biased, then the head and tail comes with equal probabilities. Yes? And this is what can be called as the quantum measurement postulate. And these probabilities are given by the Born rule. And this ends my 3-minute course on quantum mechanics. Well, it took a little bit more than 3 minutes. So the point that I want to make is that in quantum mechanics, in quantum information in general, and in particular on this bridge between quantum information and condensed matter or many body physics or few body physics, we will be using this skeletal form of quantum mechanics. This is the reason that we are able to build the bridge between a lot of systems, a lot of physical realizations of these many body systems because of the skeletal structure. It is very universally valid, this structure. So we will shift gears a little. We will talk about something called entanglement. Anindo, can you hear me?
Yes, we can hear you.
Yes, okay, thank you. So as we will see that while building this bridge, a very important concept will be entanglement. I'm sure that already in the previous talks in this series, you have heard about and learned about entanglement. But just for completeness, let me have 1 or 2 slides on what is entanglement. Again, to define entanglement in 1 or 2 slides is a difficult enterprise, but I will try to make sort of a cartoon of entanglement here. Of course, this is not a complete definition. For a complete definition, you have to look at the other talks. So what we do here, we consider 2 worlds. For entanglement, you at least need 2 systems. So these 2 systems, I call them 2 worlds. One world is full of small letters, and another world is full of capital letters. And then you see this expression. As you see that I always put the first letter as a small letter and the second letter as a capital letter. And in every term in this expression, there are 2 letters. So you have to think of them as 2 systems. And now if you look at this expression, you easily see that it can be factored like this, as a factor between small letters and capital letters. And now we can have more complicated ones like this one. And we all learned in high school that factorization can be done in several techniques. And this was one of my favorites actually in school. And you see that this one, which is more complicated than this previous one, can also be factored into small letters and capital letters. However, there are others like this one. This, Anindo, can you see my cursor?
Yes, yes.
Okay, thank you. So if you look at this one, you can easily convince yourself that this cannot be factored into smalls and capitals. Now, this simple fact, when carried over to tensor product Hilbert spaces, provides entangled states. This fact of non-factorizability of certain expressions. And now such entangled states can and has been prepared in several physical systems, atoms, ions, photons, many systems. And not only that, and there has been a lot of work on the philosophical implications, the metaphysical implications of such entangled states, the Bell theorem being a very important example. Moreover, they have been found to be useful. And as I'm sure that you must have already heard in other talks, that there are several useful properties of entangled states. Such entanglement can and has been detected, and this entanglement, entangled states, the entanglement content in these entangled states can and has been measured in experiments. Now, when you try to measure entanglement, you need an entanglement measure, you need a ruler, you need a scale, and there exists an enormous variety of entanglement measures. I'm sure that you've already heard some of them in other talks, but maybe not all, and simply because there are too many of them, and they try to quantify entanglement in different ways from different motivations. It's essentially a way by which we try to understand entanglement from different perspectives. And some important examples are distillable entanglement, entanglement cost, entanglement of formation, relative entropy of entanglement, and there are many others, many others. And these examples I have given for two-party entanglement. There are several measures for multi-party entanglement as well. By multi, I mean more than two. Yes, so this is what I was saying, that one can have entanglement between more than two subsystems, and they can also be measured. And so to see an example, if you take this state here, which is a three-party thing, where you have the first letter is a small letter, the second letter is a capital letter, and the third is a curly letter. And you can convince yourself that this also cannot be expressed as a product of smalls times capitals times curls. And this actually is has a name. It's called the Greenberger-Horn-Zeilinger state. Now, the seed for the bridge that we are about to study comes from the realization that it is only natural that the two-site and multi-site entanglement will be connected to cooperative phenomena in many body physics. Both are properties of multi-party systems, and so it is not very surprising that they will be made to talk with each other. Of course, this doesn't mean that this realization is trivial. Important realizations are always usually natural and simple. And now we have to we come to some bottlenecks The first one is that although there is a zoo of measures, there's a large number of measures of two-party and more than two-party systems, there's only a few, a very few that can actually be computed. Because entanglement measures typically involve an optimization process that is often difficult, both analytically and even numerically, analytically as well as numerically. But on the other hand, analyzing entanglement in many body systems would typically require that the entanglement be computable. I mean, if I have a physical system, I would like to know whether its entanglement is more than the entanglement of some other system. And if it can be used as a resource for doing something, then I want to know whether more entanglement would give us more facilities. So to talk about these things like this is more than this, I need to have numbers. I need to have that my entanglement in my system is 0.2 and which is smaller than the entanglement that in your system, which is, let's say, 0.3. So I need numbers. So I need to compute the entanglement. Just defining the entanglement is not enough. And that is the trouble that, as I said, that there are not so many computable measures of entanglement. But there were some cases in which one could compute, and we will discuss them now. We will discuss only the bipartite case now. We will see if we have time, we can go to the multi-party case later on. The multi-party case, of course, is much richer in span and much more difficult in analytically as well as numerically. For two parties, if the quantum state is pure, suppose I have two parties, it can be two spins, let's say two spin-half particles, or it can be a large system whose two parts I have considered. Suppose I have a system of 25 spins, but I take two parts of it. One part contains 10 spins and the other contains 15 spins. This is again a two-party system. And I also need that the entire system is in a pure state. So if I have such a situation, two parties in a pure state, then there is a good measure of entanglement. And this is simply the local von Neumann entropy. So I take the state, I find out the local density matrix of the state, of the whole pure state, and then find the von Neumann entropy of the local density matrix. Now there is a precise meaning of what do I mean by this good entanglement measure. I will not go in that direction. Simply because this is beyond the scope of this, we can go if you want at some point. So what we have is that for a pure state of arbitrary dimensions, we first find any of the local density matrices. The local density matrices of a pure state, of a bipartite pure state, have equal von Neumann entropies. So it doesn't matter which density matrix I take. I take any of the local density matrices and find out the von Neumann entropy of that density matrix. So yes, this is how you do it. You take this state, which this psi is the total pure state, and this AB is the whole system, and this A and B are the parts of it. So if I have 25 spins in the system, in the example that I told you just now, A was the part having 10 spins and B was the part having 15 spins. Or it can be that A is just a single spin-off particle and B is another spin-off particle. Whatever is the case, I take that state, psi, consider the projector of it, and then trace out any one of the parts. Here I have traced out B. the state that you get is rho A, and then I find the von Neumann entropy of rho A, which is defined like this. This base 2 is a convention. It has no physics attached to it. It is conventionally taken to be 2, so that the singlet state has entanglement 1. We have to remember that this method does not work for mixed states. It works only for pure states. The von Neumann entropy of a density matrix is the Shannon entropy of its eigenvalues. As I said, that it is customary to use the base of logarithm as 2. And the entanglement of the singlet state, as I said, becomes unity. Because, so this is the singlet state. So this is up spin and down spin. You can think of them as up and down spins in the z direction of a spin-half particle. We typically write it like this in quantum information literature. And if you trace out one of the parts, you will get a density matrix whose von Neumann entropy is 1. The local density matrices of the completely depolarized states are such that the von Neumann entropy, their von Neumann entropy are also unity. Yes, this is what I was saying, that this method of taking the von Neumann entropy of the local density matrix does not work for mixed states. So if you take the completely depolarized state, which is this, it of course is not entangled. But if you take the local density matrix and find its von Neumann entropy, it has the same local von Neumann entropy as the singlet. So we have to be careful in using this method of finding entanglement only for states for which the whole system is pure. So this was one example. We now go to the second example. So as I said, there are 2 examples that I will consider. In the first case, we considered only pure states and only bipartite systems. Here, we relax one of those constraints. We not only consider pure states, but also consider mixed states. But we put more constraints in the other direction, in the sense that not only we consider here bipartite systems, we only consider 2 spin-half particles. So in the previous case, as I was saying, A and B could have been 10 spins and 15 spins. This is not allowed here. Here A and B have to be 2 spin-half systems. Can be the polarization of 2 photons or the spins of 2 electrons. Yeah. And in this case, when you have an arbitrary state of 2 spin-half systems, there is something called the entanglement of formation that you can compute. So, but let me first define what is entanglement of formation. The definition is true for arbitrary dimensions, but it is only in 2 spin-half systems that this can be computed. So let us start. Well, a bipartite mixed state can be written as a mixture over pure states. And for bipartite pure states, there is already a good computable measure. Yes? So, yes?
Would you like to take questions in between from your chat box, maybe? Or would you like
yes,
to
yes. So I mean, I am in full screen, so I cannot see the chat box. But if you tell me the question, questions are very welcome.
The question is, this does not work for mixed states in the sense that von Neumann entropy is no more good measure of entanglement in the case of mixed state.
Yes, that is true. This is what I said. So if you look at this state, it's very clear that this is clearly a separable state. But if you look at the von Neumann entropy of the local density matrix, it is the same as for the singlet. Any other question?
No.
Okay. But this is a good question. Yes, thank you. Yeah, so I would like to tell everybody that questions are very good and actually welcome. Yeah, so I was here. So what I want to say is that if you look at this state rho AB, then I can always write it as a mixture of some pure state. Any pure mixed state can be written as a mixture of pure states. So these PIs are probabilities, they are positive and add up to 1. And the psi i's are elements of the Hilbert space in which we are working in. So the psi i's are vectors in the Hilbert space of HA tensor HB. Yes. So if HA and HB are the Hilbert spaces of the systems A and B. Yeah. So this is what I've written here. So the psi belongs to the Hilbert space, whereas this density matrix belongs to, it's an operator on the Hilbert space. Yes, it belongs to the so-called B plus H. Now, what we try to argue here is that I already know what is the entanglement of a pure state. And this is in the previous slides, we have already learned that the entanglement of a pure state is of pure bipartite state. I'm talking about only bipartite states here. Of a pure bipartite state, for a pure bipartite state, entanglement is just the local von Neumann entropy. Now, since I can write it write a mixed state like in this decomposition, why don't I define the entanglement of a mixed state like this? It's just the average of the entanglements of the decomposed states. Note the question mark here. This is not a good definition. We'll come to that. Where this E psi I is just the von Neumann entropy of the local density matrix. Yes, this I have taken the trace over B. It could have been taken trace over A, as we discussed before. Fine. But the trouble is that there is an infinite number of decompositions for any mixed state. This decomposition of a mixed state into pure state is not unique. And not only unique, it's badly infinite in the sense, I mean, this bad infinity is a colloquial term, of course. But I mean, mathematicians have levels of badness, so to say, of infinities. And this is a very bad infinity. And so this definition that we had here is nowhere complete, because I would not know in which decomposition I would have to take this sum. But we now consider that entanglement will be used as a resource for some applications. So what we do is we take a pessimistic view and say that we take the minimal over all such decompositions. Yes? And we take this, so this minimum that you see here, and this is a correct definition of entanglement, and this is called the entanglement of formation. Here is the same as before, except for this minimal thing, except for this minimization. Yes. So finally, the entanglement of formation is the average entanglement entropy minimized over all possible decomposition. Now the trouble is that this minimization is extremely difficult, and it has only been possible to do it in 2 qubits and in some other isolated examples in higher dimensions. These were done by Hill and Uters in 2 papers in 1998, Physical Review Letters both. So in all these slides, what I tried to convince you is there are 2 definite situations that are accessible to us. Accessible in the sense that the entanglement measures are computable. Number 1 is any pure bipartite state, any dimensions. but has to be pure and has to be bipartite. Number two is that any state, pure or mixed, but of 2 qubits, 2 spin halves, let's say. Now, the first papers that tried to build a bridge between quantum information and many-body physics took this second path, path number 2, this one. So we will discuss in a few slides this second path. The beginnings were slightly earlier than that, and there were important papers by many people. I have named only William Wouters and Michael Nielsen here, but these dots are important, and there are several important papers there. I have not mentioned them. And after these few initial papers...
Ujjwal, there are a couple of more questions.
Yes, tell me.
Can we measure this entanglement of formation in lab?
Yes, so there are some methods of doing it. I'm not very conversant. I'm a theorist, but I mean entanglement of formation. One way is to do tomography to find the entire state and then find it on pen and paper. That has been done, but it is experimentally difficult to do that. And the other one is to do the. And there is a method, but only theoretical. There is a proposal to find entanglement of formation directly, but the experiment to do that is difficult, and as far as I know, has not been done.
So the other question is there some physical significance to the chosen decomposition which leads to the entanglement of formation, apart from the fact that it leads to the minimization of the overall entropy?
Exactly. So this is a very good thing. So this I did not want to go into the details of that. This measure has very important properties. So one of the things is that suppose you want to prepare the state rho AB from pure states. Suppose you have a you go to a shop which sells only pure states, but you need a mixed state, and then but you would like to buy only those states which would lead you to the state rho AB at the least price, because more the entanglement, more the price of the state in that shop. So in this sense, what we find is that this decomposition gives us the minimal cost of creating entanglement, creating the state rho AB in terms of entanglement. There is a slight amount of cheating here. This is not really entanglement cost. Entanglement cost has to be defined in a more complicated way, but I will leave there. Any more questions?
No.
Okay. Yeah, so after these few initial papers, there was a couple of papers, these two papers, and they were trailblazing, to be precise. And so one was by these people, Osterloh, Amico, Falsi, and Fazio, and the other was by Osborne and Nielsen. And they both considered entanglement in close to a quantum phase transition. And the subject had a huge number of research groups working in that. And here are some reviews. Of course, these reviews are already old. There are newer reviews probably. I am not very conversant with these reviews, newer ones. But let us look at these two papers. I will look at mainly this first paper. The second paper is sort of similar. So if you remember, we are following the second path. Yeah, we had talked about two paths. If you remember, can we go? Yeah, so you had two paths. we are talking about the second path. We will go to the first part after a few slides. Yeah. So what do you do in the second path? Well, you find an interesting state. What does it mean by an interesting state? From many body perspective, it can be the ground state or the thermal state or some time evolved state of a system of qubits. Two-dimensional systems can be spins half. And if I want to find such a state, for example, if I want to find the thermal state, I have to diagonalize the Hamiltonian. So this system, I have to know the Hamiltonian. I have to find its states, the thermal state or the ground state or some other state. And then what I do, I trace out all the parties, all the qubits, except a specific two. Say some nearest neighbor qubits. So I'm imagining that this system is on a lattice, and on that lattice these spins are marked as 1, 2, 3, 4 up to n, and let us say that 1 and 2 are side by side to each other, and I find out the ground state of that system. After finding the state, that state is an n-party system, it's an n-qubit system, and then I trace out everything except the parties 1 and 2. I get a state that is a 2-qubit state. Yes, 1 and 2 are each qubits. So the state that I get after tracing out is a 2-qubit state. Now I find the entanglement of that 2-qubit state. Now this 2-qubit state that I get after tracing out can be mixed, can be pure as well, but in most cases it will be mixed. But we have just seen, and this was the second path, that 2-qubit state, whatever the state is, I can find its entanglement in the sense that I can find its entanglement of formation. And then I analyze that entanglement of formation with respect to some system parameter. So for example, in condensed matter physics, people usually find some driving field, the system has a driving field, and there are some interesting things that happen, a phase transition, for example, that happens as you change that driving field, as you crank up or crank down that driving field. So I look at the behavior of entanglement of these 2-qubit states as I change the driving field. For example, I can change anything else, but for an example, I'm taking the driving field. So let us take an example, and this example is exactly this paper by Osterlo, Amico, Falsi, and Fazio in Nature. This is a many-body system. This is a very standard many-body system. Many people, whenever they have a new topic in quantum condensed matter, they often begin their survey or analysis by using this many-body system. It's the so-called XY model, the transverse XY model. So it's called XY because you see that there are interactions in the X direction and Y direction, and it's transverse XY because there's a transverse field. Yes, so it's called the transverse XY field. It's also called anisotropic transverse XY field, transverse XY model, because there is this difference between the power of the interaction and the strength of the interaction in the X direction and Y direction. This anisotropy is quantified by this quantity gamma. Yes. This J is the coupling strength. Well, this J by 2 multiplied by 1 minus gamma and J by 2 multiplied by 1 plus gamma are the coupling strengths in the X and Y direction. But for short, we will call this J as the coupling strength. And this H is our driving field. So what we do, well, what they did, Fazio and others, they found the ground state of this model. This model is exactly solvable and one can find the ground state exactly. They traced out all the qubits except two nearest neighbors. Yeah, I mean, you take a pair of nearest neighbors. Now, they considered periodic boundary conditions, and therefore it doesn't matter which nearest neighbors are considered. And because this is a model of n spin half particles, this nearest neighbor state that you find is a 2-qubit state, so that its entanglement of formation can be found. So what they did is that they found this entanglement of formation and analyzed it as you change the ratio between this coupling strength J and the driving field H for a fixed value of gamma. And this is the result. So this lambda here is this J over 2H. And then this the first look at this smaller figure here. In this case, the number of particles is infinite. And this is the lambda, the J by 2H. And this axis is the entanglement of formation. It is not exactly the entanglement of formation. It's something called concurrence, which is a function of the entanglement of formation. And they found this feature. Then, in the bigger plot, they used the horizontal axis remains the same as here and here, but the vertical axis is now that derivative with respect to lambda, the area of in the domain of area law. So when they say that they are talking about how the entanglement scales, they actually mean that the behavior, how SL behaves with respect to L. So, and what they find is that for a large number of systems, entanglement scales as the area of the smaller system. So here we had a larger system and a smaller system. The smaller system has size n, and the larger system is the bigger one, the n, or rather it's not really n, it's capital N minus small n, that is the smaller system, larger system. The smaller system is small n. Now, what they found is that for a large number of physical systems, this SL scales as the area of the smaller system. But this happens only if we are away from any phase transition that is in the system. If there is a quantum phase transition in the system, we have to be away from it. And only then we will see this feature. So now if you are in a 1D system, in a one-dimensional system, in the sense that if the Hamiltonian is defined on a lattice that is one-dimensional. So in the model that we discussed, the Hamiltonian that I showed you, that was a 1D system that was on a chain, so to say. The entanglement should remain a constant with respect to the size of the smaller system. In 2D, the same would scale as the characteristic length of the smaller system. So to give you the formulas, it looks like this. So this SL would scale, this is the demand in this, so the area law says that if you are away from a quantum phase transition, then the SL would scale as capital L power d minus 1, where this capital L is the characteristic length of the smaller system. Pardon? No, sorry.
There is a question.
Yes, yes.
What do you mean by phase transition exactly? Since you are talking about one-dimensional case similar to Ising model, in which phase transition does not take place.
So I think there is some confusion here about phase transition. So here, of course, I am not in a position now to define quantum phase transitions. The transverse XY model, the quantum transverse XY model in one dimension does have a quantum phase transition in it. It goes from the antiferromagnetic phase to the paramagnetic phase. But I mean, I don't have chalk and board, so I cannot, of course, and also there's not so much time to go into the details of that model to define what the phase transition is in that model. But I mean, you can go to any book on quantum phase transitions or statistical mechanics essentially, and find that this model does have a phase transition. It's actually arguably the simplest quantum model that has a quantum phase transition. Yeah, any other question?
No.
Yeah. So the thing that I said about areal law, if I want to write it in a mathematical form, it looks like this. So this SL, so if you remember, this L was the running index of my smaller system. Yes. So the smaller system goes until the size goes up until n, but I want to change I want to see the behavior of SL as the size of the smaller system changes, and that changing size is denoted by this L. And so that is this SL. And this SL, you have to remember that, yes, this is the von Neumann entropy of the smaller system, but it is also the entanglement of the smaller system versus the bigger system, provided the entire system is pure. Sorry. And this L is the characteristic length of the smaller system. Now, if it's a 1D system, that L and small l and capital L are the same. But if it's not a 1D system, then they are different, of course. Capital D is the dimension of the lattice. So for a one-dimensional lattice, this capital D is 1, and the capital L is equal to small l. But for a 2D lattice, the capital D is 2, and capital L is L power half. Yes, I mean, it's not equal. This equality was not very correct. I mean, it's of the order of L power half. There can be some, I mean, it's a triangle, there is a 1 by root 2 there, and so on. Now, all this was near a quanta, all this was away from a phase transition, quantum phase transition. If we are near a quantum phase transition, then there is a corrective term in the area law, is a corrective multiplicative term that is proportional to the logarithm of the characteristic length of the smaller system. And yes, this is the one. So when we are away from a phase transition, this log L term is not there. But as we approach as we come very near to the phase transition, we see this type of a behavior. So we have to remember here that this area law does not hold for all systems. It holds only for, it holds for a large number of systems, but not for all. Okay. And so for the systems that for which it does hold, what it seems that the scaling of entanglement with respect to smaller system can be a signature of a quantum phase transition. And so the very first paper so all these things that I said began with this paper that you see here by Vidal, Latorre, Rico, and Kitaev in this paper in 2003, where they considered some examples of physical systems for which this area law does hold. So this is the so-called XXZ model. So you have this XX and YY interactions, and this Z interaction has an anisotropy, delta, and there is a transverse field. And this is the XY model that we already considered, well, with some change in notation. Yes. And this is the figure. Sorry, somehow the colors have vanished. Uh, or no, maybe there were no colors. So if you look at these two curves, so this empty squares is the Ising chain, the transverse Ising chain, where and this is the number of sites. This axis is the number of sites. So this is the system size. No, sorry. The system size is kept at very large number. This L is the small l in our notation. Okay, so I'm sorry for this change in notation. Instead, so I was using this SL. If you remember the small l, here they are using capital L for that. So this capital L here is the running index of the small system size. Okay, where the actual system size is kept at a very large number. I forgot that number actually. Sorry, I don't remember that number, but that is kept at a large number. And this is the running index of the small system. And this curve of this empty squares, this curve is for the non-critical Ising chain. So the gamma is kept at 1. The gamma is the anisotropy. So this gamma is kept at 1. So there's only the XX interaction and the transverse field. And A is kept at 1.1. So you remember that there is a phase transition in this model, but this A equals 1.1 is not at the phase transition. It is away from the phase transition. And there, what you see is that the entanglement, the entropy of this, so if you look at this box, let's say this box here is the entropy of a smaller system, where the smaller system has size 10 and the larger system is very large. And so this indicates, this point, this square here indicates the entanglement between 10 spins and the rest, and so on. What you see is that this entanglement comes to it converges to a constant. Now, if you look at this formula here, you come here and you see that D is 1 in a one-dimensional system, and so the area law dictates that the entropy of the entanglement should become a constant if we are away from a transition. Sorry. And this is what we see here, the entanglement converging. But now instead, if you go to the stars is for the same system, but the A is chosen in such a way that you are at the transition. And there you see a logarithmic divergence. So if you fit the curve, it's exactly log L. And the other curves, curves are for the other model. Let me not go there. So what we saw here is that, so what we exactly saw here, this is what we advertised, and we saw in this example of the transverse XY model that the scaling of entanglement, which here means that the behavior of the von Neumann entropy of a small system as the system size increases with respect to the smaller system size can be a signature of a quantum phase transition. Are there any questions?
No.
Okay. Now, as I said, these were the very initial papers. the first that considered these two paths, this so-called first path and second path. And there were several other directions that were explored. Many other models were considered, and several different quantum correlations were analyzed, and even quantities that are not quantum correlations were also analyzed. And there are a large number of very nice papers on ground states and thermal states of the system. But let us travel off that road. So we go to something else that does not consider ground states and thermal states. So there are maybe a very few papers that consider, instead of the ground state, they consider the excited state. This is a non-trivial question in the sense that usually in condensed matter physics or in ultra-cold gases, people consider either the ground state or the thermal state. However, current experiments make it possible in some situations that even excited states can also be considered experimentally. So this calls for the question that we have as the title of this slide is that what if we analyze the behavior of entanglement or some similar quantum correlations for an excited state and not for the ground state. And so this model that you see here is, so this is the Heisenberg interaction, where this vector notation here is for a triad of Pauli matrices. And this is at site I, and this is at site the next site. And this is in one dimension. This is called the J1, J2 model. And the interaction J1 is the interaction strength for the nearest neighbor coupling. And this is the next nearest neighbor coupling. And the coupling here is J2. This is sort of a quasi 1D model because of the existence of this next nearest neighbor interaction. For J2 equals half of J1, this model is exactly solvable and is called the Majumdar-Ghosh model for the people who solve that model. Now, this model is known to have a phase transition at J2 by J1 equals around 0.24. And this is already known from other order parameters. But analysis of the bipartite as well as multipartite entanglement measures did not lead to an identification of this transition. So people did some analysis, including in our group. We analyzed this model, but we analyzed the bipartite as well as multipartite entanglement. And we saw that this is not easy to identify this transition in this model by using such entanglement. But these analyses were all for the ground state. In this paper, which is by your organizers, well, one of your organizers, and they change tax, and they ask this exact question, that what if we consider the first excited state of this model instead of the ground state? And there they found that indeed the nearest neighbor bipartite entanglement of the first excited state of the J1, J2 model can be an indicator of the transition of this model at J2 by J1 equals 0.24. It's not exactly 0.24, it's 0.24 something. I'm just writing 0.24. Well, this was one direction. One more direction that I want to consider is the entanglement in time evolved states. So the ground state as well as the excited state and also the thermal state, they are the so-called static states of the system. They do not evolve in time. But what if we consider the evolution of the system from a state that is not its eigenstate? So I somehow do something to the Hamiltonian so that the system moves out of equilibrium. And then the system will evolve in time. And then can I see something in the evolved state of the system with respect to its entanglement behavior? And this is one paper where they considered that. There are several papers that have done that. I have taken just this example, where they again consider the nearest neighbor entanglement. In this case, they consider something called the logarithmic negativity of the nearest neighbor entanglement. We have not discussed what is logarithmic negativity. It is another measure of entanglement. They have taken the anisotropy at 0.5. Now what they do is that they take the equilibrium state of the system at a given value of the transverse field, and then at the initial time, they change that initial field to a different value. And now, of course, with respect to that changed value of the transverse field, the system is no more in equilibrium. It is out of equilibrium. So it will evolve. And now what is shown in this figure is the behavior of entanglement in that evolved state. So on this axis is time, and on this axis is the value of that initial entanglement. So here what they consider is that they take the initial value of the field to be this value A, and then for all later times the field is taken to be 0. And this z-axis, the vertical axis, is of logarithmic negativity of the nearest neighbor state. And this shows this behavior where you see that so you remember that the entanglement of the ground state also had behavior that is sort of seen here. So this behavior we have already, so this at time t equal to 0 is the same behavior that we have already seen in the previous, in one of the previous slides in this Nature paper, and it showed this behavior. Now what we see here is that as time evolves, this zero, there is a 0 entanglement here that becomes a range of 0, and that broadens out into sort of a sea of entanglement. So there is a river of 0 entanglement that goes into a sea of 0 entanglement here. So the black portion is the portion where the state is separable, so that there is no entanglement. So this is the reference where this is done way back in 2005. Any question?
No.
Okay. So we will we have discussed some aspects by which some ways by which quantum information has been connected to many body physics. If there is time later on, we will discuss a few more. But for the time being, we shift to a new direction where people have connected quantum information with few body physics. This has different. The importance of doing that, well, is first of all gives us fundamental knowledge about both quantum information as well about the few body physics systems. But also, if we look at the recent experimental capabilities that we have, well, we in the sense, not me, the experimentalists have, then you realize that few body systems are more controllable than a many body system, for obvious reasons. I mean, if you have a large system, then it is difficult to control. So suppose you realize a many body system in an ion trap, then to prepare a 16 qubit ion trap and control it is much more difficult than to control 3. So there is a practical as well as a fundamental aspect of this connection between quantum information and few body physics. So we will have a few examples of this connection. And the first one is about what can be called quantum refrigerators. Well, it all began with this paper by Linden, Popescu, and it's difficult for me to pronounce this, Shepshek, in 2010. Well, we will actually deal with a 3 qubit system, but let us first begin with 2 qubits. So let us consider a situation where 2 qubits, 2 spin halves, 2 spins half are immersed in the same bath. The bath is at a temperature Tr. So this qubit 1 we will call as the cold qubit, in the sense that this is the qubit that we will cool down. And the qubit 2 will take the role of a spiral, the same role as the spiral has in a refrigerator. It will take heat from qubit 1 and dissipate it into the environment. So the Hamiltonian, the free Hamiltonian of the system looks like this. So this pi 1 is of the first qubit and pi 2 is of the second qubit, where this pi 1 is this. So the ground state has 0 energy, and the excited state has energy E1 for the first qubit. And for the second qubit, the ground state energy is again 0, but the excited state has energy E2. And so for cooling the qubit 1, we will increase the ground state probability. We will try to increase the ground state probability of qubit 1. So what we will do, we will transfer the excitations to qubit 2. Now we choose our Hamiltonian, we choose our setting in such a way that this E2 is greater than E1. You remember this E2 and E1 here? So this E2 was the energy of the energy gap of the second system and the second qubit, and this E1 is the energy gap between the ground and excited states of the first qubit. Now you can show by simple algebra that if E2 is greater than E1, then in the equilibrium state, the state 1, 0 is more likely than 0, 1. It has a higher probability of occurring if the whole system is in the equilibrium state.
So at equilibrium, qubit 1, this is the qubit to be cooled, is more likely to be in the excited state than the other qubit. We now apply an unitary that does the interchange 10 to 01 and vice versa, so that qubit 1 is cooled. Yes, so here this 1 is of the first qubit, 0 is of the second qubit, and we saw that the system is more likely to be in this state because E2 is greater than E1. So we apply the unitary, it goes there, where qubit 1 goes to state 0, the ground state. So qubit 1 is cooled in this way. Now if you do nothing else, after applying this unitary, the qubits will again return to the temperature TR of the bath. Yes, this is what statistical mechanics teaches us. Under certain assumptions, everything goes to the equilibrium state at the temperature of the bath. However, if we keep repeating U many times, we will reach a steady state where the temperature of the qubit 1 will be less than TR. Well, pardon my notation, I mean this TR is T suffix R, okay? So this TR is, so you remember what we are doing? We have 2 qubits and we have a single bath, and that single bath is at temperature TR. Now we are applying U many times. So the system is going out of equilibrium and it is not getting time enough to come back to equilibrium because we are keeping on applying U many times. So the system will evolve and finally go to a steady state. And I am not showing you the algebra, but you can show, and these people have shown, that in the steady state, the temperature of qubit 1 will be less than the temperature of the bath, and that of qubit 2 will be more than the temperature of the bath. And this is the typical refrigerator, yes? However, this requires external work because this E2 is greater than E1, and so in this states that are there in the unitary, we want to change 01 to 10 and vice versa. They have different energies. So if you want to go from one state to another which has different energy, you have to perform external work on the system. So although this is a refrigerator, this requires external work. We'll try to see what we can do about it. Questions?
There is a question.
Yes.
Why don't we go for E2 less than E1?
It's exactly, it doesn't work. That's the point. I mean, the point is that it is when E2 is greater than E1, this refrigerator works. You can cool down only when this E2 is greater than E1. So this is a requirement of the system. It's like you have to keep the fridge door closed to keep the fridge working. Any more?
No.
Okay. So now we consider, and so this is we are still in that paper of Linden and others. What we consider now is slightly different thing, but with a very important implication. And it is called a self-contained quantum refrigerator. We will see what it means. So the idea of a self-contained quantum refrigerator is to provide a third qubit. We already had 2 qubits. We provide a third one. And the third, again, has zero energy in the ground state and now has an energy E3 in the excited state, such that E3 is exactly equal to the difference between the energies E2 and E1. Now you can see.
I may interrupt. There is another question.
Yes.
If the environment is the sink, what is the source in this refrigerator?
So the source, so in the previous refrigerator, right, the source is exactly the unitary operation. So this is, so you are performing work, and that is how you are, the environment is the sink. So
There
now,
is another.
Yes.
If E2 is less than E1,
Mm-hmm.
then 0, 1, the state 0, 1 will be more probable than 1, 0. From what you have said earlier, will this not cool the first qubit?
It will not cool. It will, I mean, the roles of qubits 1 and 2 will be reversed. So now qubit 2 will be cooled and qubit, so you have to apply, is the same method will work, but only the roles will be reversed. So it's the outside of the fridge that will be cooled and not the inside. So if I want to use a cartoon.
So I think he is following up with, we won't apply U afterwards.
Yeah, so let's go on with this.
Yeah, maybe should I ask him to unmute and
Yeah, we can take the question at the end. I mean,
okay.
I mean, all questions are allowed. I mean, you can ask questions in between, but I mean, because this question I don't understand, so we can take that at the end.
Okay.
So, are there more questions?
No.
Okay. So, as I was saying, that the idea of self-contained quantum refrigerators is to provide a third qubit, so that the energy gap of that qubit, of the third qubit, is exactly equal to the difference in the energy gaps of the other two qubits. And now, with that, if you put that constraint, you will find that these two states are degenerate. They have the same energy. And so a unitary swapping them can be performed without external work. And in particular can be performed even without external control if I use this Hamiltonian, where this G is the coupling strength of the interaction between the qubits. So this is a interaction between the three qubits that is making up the refrigerator. And there is a reason for that this EI has to be much larger than the G, because otherwise the equilibrium constraint will not hold. So one has to satisfy this so that the refrigerator works. And this is a picture from their paper. So you remember that this qubits 1 and 2 are connected to heat bath that has temperature TR, and now there is a new qubit. This one is in contact with heat bath that has temperature TH. Pardon me, that this H should be in the suffix. So this is the picture where this, on the horizontal axis, there is this TH. This is the temperature of the heat bath to which qubit 3 is in contact with. And this vertical axis is the difference between T1S and TC. So let me define what these are. So this T1S is the steady state temperature of the qubit 1. This is the qubit that I want to cool down. And this Tc is the temperature of the heat bath with which that qubit 1 is in contact with. Now, until now, we have denoted this Tc by Tr. I will tell you why they have used the different notation. For the statement that I want to make now, just ignore this suffix Tc, the C suffix, and just think of it as R. Okay? So this is T1s minus Tr, and on this axis is Th. Now, look at this blue solid curve. Now, as you see that this line is the 0 line, and after this point, which is at 2, after that point, this term becomes negative. So the steady state temperature becomes lower than the temperature of the bath with which it is in contact with. And this is exactly the condition of a refrigerator. So we have been able, so when, for example, TH is at 2.5, so this TH is the temperature of the heat bath with which qubit 3 is in contact with. When we are at 2.5, then we have been able to cool down qubit 1 to a temperature about minus. So temperature is of course not minus. I mean the T1s minus Tc is minus 0.1, I guess. Yes. Whereas for this curve, this Tc, which for our purposes now is Tr, this is at 2. So Tc is 2, and so this difference is 0.1. So we have been able to cool down qubit 1 to a temperature 1.9. Whereas the bath with which it is in contact with is at temperature 2. It is at a higher temperature. So we have been able to cool down the qubit 1 to a temperature that is lower than its environment. So, and now we go to the other curves, and there we will need this notation Tc. They go to a more general situation where the qubit 1 is in contact with a separate bath which has a temperature Tc. And then they consider different cases, and in all these cases, except of course in the case where this Th is equal to Tr, in all the other cases they have been able to obtain cooling, but with different amounts. And it goes, the cooling happens at larger temperatures of the bath of the qubit 3. So for example, for this green curve, one has to go to a temperature around 2.6 or something like that to get cooling. But it does appear in all cases. An important question that people ask in these papers on the refrigerator is, what is the resource that is necessary for attaining refrigeration? There are several candidates. People considered coherence as well as entanglement and even multi-party entanglement. But the final answer is, as far as I know, not very clear as yet. Is there any more question?
There are a couple of questions, but you could take it at the end. The participants could ask themselves, Prem Kumar and Jatin Ghai. Jatin Ghai has a follow-up question, and Prem Kumar has a question.
Okay. So I am also running out of time. Maybe
I stop here, and will discuss the rest of the quantum refrigerator tomorrow, day after tomorrow, and I
Yes.
take up the question maybe. Yeah.
Yes. So, Prem Kumar, if you could unmute yourself and please ask the question.
Sir, what I was saying that from what you have said, if E2 is less than E1, then
Mhm.
0, 1 state will be more probable than 1, 0 state.
Mhm.
And this will automatically cool the first qubit. We don't need to apply any flip unitary operation afterwards.
No. So this is the point, that I mean, if you already have a cold qubit, you will not need to cool it, of course. I mean, if you are already in a very cold climate, then you don't use the refrigerator. So that's the point. So we are trying to set up a situation in which a qubit is hot and we want to cool it down. If the qubit is already cold, we will not cool it down. We will just keep it as it is.
Okay, sir. Thank you.
Okay. Yeah.
Jatin Ghai, you could unmute yourself and.
So, sir, I was saying the unitary is applied by us. It is like a working source, like we have a working source in normal refrigerator. It acts like a working source here. So, what
Yes.
exactly is the source, the heat source? I mean, what we have in usual refrigerator.
Yeah, so this is so the work that they have done in this paper by Linden and others, that is on the on self-contained quantum refrigerators. The previous refrigerator that I talked about, this people knew probably already before, and this is not the content of that paper. So this this refrigerator works obviously because you are applying work from outside, and by using that work you are cooling down a qubit. That is not so important. The importance comes only when you come to a self-contained quantum refrigerator. The previous discussion I thought was useful to sort of motivate the self-contained refrigerator. So to answer your question, I would say that there is a sink, which is the bath, and but the second law is not violated because you are applying water. Okay. Any more questions?
No, there appears to be no more questions.
Okay. So thank you. We meet day after tomorrow.
Yeah, we'll meet day after tomorrow, that is Saturday at 3 o'clock.
3 o'clock. Yes.
Thank you, Ujjwal.
Thank you. Thank you. Thank you. Thank you very much.